in last class we have demonstrated Malus law, means if unpolarized light is polarized using the polarizer, now if you use another polarizer as an analyzer and rotate that polarizer analyzer with respect to that polarizer. So, polarizer and analyzer both are basically same, just the name are different because of the use. So, they have optics axis. So, this electric field, that vibration, it's basically pass along the optics axis. Okay. So, so it gives the plane polarized light. So, it has electric field component, it's vibrating in a particular direction. Now, if you use another polarizer as analyzer, so keeping the optics axis parallel to the optics axis of polarizer. Okay. So, that means this light, this polarized light, this electric component, it will pass through it. Okay. So, we will get the intensity of the light. So, that is basically square of the amplitude. So, that is if it is E0, so E0 square will be the intensity of light. So, that intensity of light we detected using the detector, photo detector. Okay. So, now when we rotate the analyzer, so it will make angle, this optics axis of the analyzer will make angle with the optics axis of the polarizer. So, if it is theta, so then component E0 cos theta, that is the component will pass through the analyzer. Okay. So, its intensity will be E0 square cos square theta, E0 square is I0. So, basically intensity I will be equal to the I0 cos square theta. So, that experiment, this is the Malus law, and that we have verified in last class. We have demonstrated the experiment. So, so when you are using polarizer analyzer, so we are telling that we are getting polarized light. Now, what is the mechanism for polarization of light? How we can produce polarized light? Okay. So, that is what I will discuss today, and we will demonstrate one experiment, that is basically Brewster's law. So, let me tell about the theory of that experiment, and then we will demonstrate the experiment. Okay. So, polarization of light, right. So, either polarizer or analyzer, it works on some principle. Okay, to polarize the light. So, here that is what in general I am discussing, how we can polarize the light. Okay, or how polarizer polarize the light. Okay. What is there, what we use as a polarizer. Okay. So, almost all sources emit unpolarized light, right. So, unpolarized light so its electric component it's vibrate in all directions. So, we expressed this with two mutually perpendicular component, that is this plane is perpendicular to the direction of the light. Okay. And that also we represent like this. So, one component is another component is perpendicular to the paper. Okay. So, how to produce polarized light and how to manipulate the polarization state. Okay. Polarization state. So, so this light is this is the propagation direction. So, if this is the direction of the electric component, okay, then we tell it is a polarized light. And this type of polarized light, when plane of polarization means this, the plane contain the electric component, direction of the electric component, and the direction of the light propagation. So they are on this plane. So this is the plane of, so this we tell the plane of polarization, okay. So if plane of polarization, this plane is same as the plane of incidence, okay. So light is falling and then it's refracted or reflected, so normal is there, so that the plane of incidence, okay. If plane of incidence and plane of polarization is same, then we tell that's the pi polarization, okay. So that we tell the pi polarization. If plane of polarization is perpendicular to the plane of incidence, okay. So in this case, if this is the plane of incidence, okay, and then plane of polarization, actually this, it's basically contain the direction of the electric field as well as direction of the propagation of light. So they are on this plane, So if this is the plane of incidence, then plane of polarization is this, okay. If they are perpendicular to each other, then we tell that is the sigma polarization, okay. So this plane of this paper, if we consider is the plane of incidence, then pi polarization we represent like this, and sigma polarization we represent like this, okay. So now there are essentially 4 methods to produce polarized light from unpolarized light. So dichroism, scattering, reflection, and birefringes. Birefringes or birefringes, people tell different way, or it is called also double refraction, okay. So there are 4 methods, okay. So tourmaline is a dichroic crystal. This is a natural crystal, is called tourmaline, okay. So this crystal actually it can, so this crystal basically have optics axis or pass axis. So means it depends on the which axis, which direction will be optics axis or pass axis. It depends on the structure of this of the crystal, okay. So one direction is the optics axis or pass axis, means the electric field parallel to this electric field, that component parallel to the optics axis will pass through, and electric field perpendicular to the optics axis, that will be obstacled, will not be passed through, okay. So if this is the optics axis for this tourmaline crystal, so unpolarized light is falling on this, then we will get only this electric component, other one this will be discarded. So other side of this crystal will get polarized light, right. So this is one way. So this is called dichroic crystal. So it's a natural crystal, and one has to cut the crystal in proper way, identifying the optics axis, okay, and one can use as a for polarizing the light. So, this mechanism is called the dichroism. Okay. So that means this sheet actually one can use as a polarizer or analyzer, right. So another method is scattering. So sunlight is coming, there are a lot of dust particles or molecules in air. Okay. So this sunlight scattered fall on the air particle. Okay. And then so that air particle, air molecule that acts as a scattering center. So any particle, any molecule, they have electrons. So basically there will be dipole oscillation. Okay. So if this is the direction of dipole oscillation, along this there is no radiation. Okay. Along this there is no radiation, right. So radiation is maximum perpendicular to this direction, right. So when this unpolarized light is falling, so actually one component, so because of the directional oscillation of the dipole of air molecule. Okay. So one of the component will be scattered and other of the component will not be scattered. Okay. So whatever the scattered light you will get, then it will be polarized. So it may be partially polarized. So but after scattering with many particles, so finally one can get the polarized light. So scattering also another reason to polarize the light. Okay. Third is reflection, and fourth is birefringence or double crystal, double refraction. Okay. So these two are very important method. Generally most of the device based on this polarizing device based on this two method. Okay. So we'll demonstrate, experiment and discuss them in details when we'll plan to demonstrate experiment based on them, and for that we'll discuss about it. So these are general discussion I made. Now let's so let's see this polarization by the reflection, and we'll do one experiment based on this. So polarization by reflection. So this is a glass slab. Okay. So unpolarized light is falling on it. This is the normal. Now one part is reflected, another part is refracted. If you change the incidence angle, so actually both reflected light and refracted light both are unpolarized light. If you change the incident angle, and for a particular incident angle, so this reflected light, it becomes polarized. This reflected light becomes polarized, although this refracted one is unpolarized or partially polarized. So this is basically sigma polarized light we get. When we get for a particular incident angle. So that incident angle is called basically Brewster's angle. Okay. So he discovered this method, he found this method, and he also found that this at Brewster's angle, incident angle, will get reflected, polarized reflected light, and at that condition, at that position, the angle between the reflected light and refracted line is 90 degree, okay. So, so from Snell's law, actually sin theta by sin phi, this is the refracted angle equal to mu, refractive index of this glass, okay. Now, in this condition, under this condition at Brewster's angle, basically we can write this theta plus 90 degree plus phi equal to 180 degree, So, theta plus phi is 90 degree, okay. So, phi equal to 90 degree minus theta. So, sin phi equal to cos theta, right. So, here sin phi we can replace with the cos theta. So, mu equal to sin theta by cos theta equal to tan theta. So, so this angle theta, we tell this Brewster's angle. So, this angle theta b equal to tan inverse mu, okay. So, if you know the refractive index of this glass, you can find out the Brewster's angle, or if you can measure the Brewster's angle, okay, you can find out the refractive index of this glass, okay. So, so this experiment, so we will demonstrate this experiment in the lab. So, experiment is basically the verify the Brewster's law, okay. What is Brewster's law? At a particular angle, at a particular incident angle, the reflected light will be polarized, okay, and find out the refractive index of the material of glass. In that condition, if you can measure the Brewster's angle, then we will be able to find out the refractive index of the metal of glass, right. So, aim of the experiment is at Brewster's angle, the reflected rays are polarized, that we have to show. How to show that I will discuss. Measurement of Brewster's angle and calculate the mu equal to tan theta b, okay. So, this is the experiment we will perform in the lab. So, let us how to do this experiment, let us follow the procedure step by step. So, we will use prism table and we will use prism or glass slab, one also can use glass slab, okay. But we will use prism on surface, refracting surface of the prism we will use because we will look at the reflected light, okay. We will look at the refracted light. So, so first we have to make ready the prism spectrometer for parallel rays and image of slit source on the crosswire of the eyepiece of the telescope. So, you know, we have demonstrated many experiments using the spectrometer. So, initially we have to make ready the spectrometer, labeling the spectrometer, then using the spirit level, then we will use the optical leveling, then we will use the Schuster's method, okay, for getting the parallel rays and focusing the eyepiece, okay, to the crosswire, okay. So, so when the spectrometer is ready for doing experiment, then we then find the incident angle for which a dark view eyepiece for a particular position of polarizer light on computer. Okay. So, what we will do? So, on prism table we will put this prism. So, this reflecting surface we will use, okay. So, from collimator parallel rays will fall on it and then this is the reflected, okay. we will put the telescope here. Okay. Now, now which one is incident angle? Basically, this is the ray, and if you this is the perpendicular to this to this face. Okay. So this will be incident angle. Now, if I rotate the prism, so I can change the incident angle. So initially I will, so if this is the normal, so initially I will rotate the prism to keep this angle is almost 0. Okay. Now I will increase the angle, I will increase the angle, I will increase the angle. So almost 0 means, so for my telescope will be here. So now you know this, if I rotate the mirror by angle theta, so I have to rotate this telescope to see the reflected one by 2 theta. So that means this whatever incident angle you will change, so that to get the polarized light in telescope, so you have to rotate the telescope by 2 theta angle, right. So actually for each incident angle, we will catch the reflected one, and then that reflected one is whether it is polarized or not. For to check that one, what we have to do, we will use one analyzer or polarizer, okay, in front of this telescope. Now we'll rotate these polarizers with a complete one rotation. So if we see that, okay, intensity are not changing, so that means it's unpolarized. If intensity is changing with rotation of the polarizer, so we can say that this is the partially polarized. So when it will be, we'll change the incident angle, and we'll catch the refracted rays, and we'll continue this procedure, for a complete rotation of the polarizer. What we have to get, if it is completely polarized, so one position of the polarizer will get this, there will be no light passing through this telescope, so this view will be dark. So that means this polarizer have optics axis. When it is completely polarized, okay, so when optics axis is perpendicular to the direction of the electric component, then there will not be any electric component, means light will pass through it. Okay. So we have to change the incident angle, and for each incident angle we have to catch the reflected rays in the telescope, and for each reflected rays we have to do this one complete rotation of the polarizer, and we have to see whether we are seeing that field of view is dark, whether getting during the rotation, whether we are getting one complete, for a particular position we are getting complete dark field of view. Okay. When we will get complete dark of view, that means this reflected light is completely polarized. And now we have to measure so then at that position we will take the reading of this telescope, Now we will take out this prism, and then we will take the reading of the direct light. Okay. So we will note down that one. So this will be, so basically then what is happening? So this reading and this reading we are taking, so this is the angle, right? We are measuring, we are getting from the reading of the telescope. Now here this is the incident and the refracted. Okay. So that means this normal is here. So that means this angle, if it is incident angle, then this will be reflected. So these two total angle is basically 2 theta, right, or 2 theta b, we can say 2 theta b. So, 2 theta b plus this angle phi, whatever we have measured, so that will be 180 degree. So, then theta b is 90 degree minus phi by 2. Okay. So, experimentally we are measuring phi, So, if you put phi here, so you will get theta b. Now, when you will get theta b, so you can calculate the mu. Okay. So, for that we will use table. So we have to find out Vernier constant. 2 Verniers are there in spectrometer, you know. So, Vernier 1 and Vernier 2. So, you have to note down, generally both are having the same Vernier constant. Note down the Vernier constant. Then your CDL number means number of observation 1, 2, 3. Okay. So, that means for each incident angle you are checking. Okay. So, telescope reading for complete extinction of reflection. So, basically we'll do this process, okay, for each change of incident angle. We'll catch the reflected one and we'll rotate the polarizer, and if it is not completely dark, means complete extinction of the reflected light, so that reading we are not noting down. Okay. So, when we will get complete extinction of reflected light, so that reading we will note down for Vernier 1 and Vernier 2. Okay. So, similarly 2 more observation we will do, repeat the experiment basically. You know this, we take more data, more observation, so it will be more accurate. So, for each then for each time basically we'll take one set data and then we'll remove the prism, and then we'll take direct reading, okay, and then again we'll put prism, take the second data. So, that way 3 times if you take, then that will be really, sometimes people what they do, that first this 3 times they are taking this one and then next 3 times they are taking this one. So, that is not the good way to do anyway. So, then you find out the difference of A and B. So, that will be phi. So, mean phi you can find out. So, theta b you can find out. Okay. So, that's what the experiment, verification of Brewster's law, and find out the refractive index of the material, of the prism or the just glass slab. So that's what one has to do, and I think in next class I will demonstrate the experiment in our lab. Thank you for your attention.